Okay, welcome back. Now let's finally start putting things together so that we can do some calculations so you can see how these things affect each other and we can start making some flow charts. So to do that, let's talk about something called stroke volume. And stroke volume basically is the volume of blood that's ejected from the ventricle with every heartbeat. Now you need to realize that what is exiting the right ventricle is exactly the same that is exiting the left ventricle. Only we typically just use the left ventricle because that's where it's easy for us to measure it. So when we look at the heart, at the end of diastole in the ventricles, so the ventricles have been there and they have been relaxed, and the atria are relaxed at first, and the tricuspid and mitral valves are open, so blood's pouring into the ventricles from the atrium. Then we have atrial systole pushing those last droplets of blood into the ventricle. So that last moment before the ventricle starts systole is called the end diastolic volume. That's how much blood is in the ventricle before the ventricle contracts. So that's the maximum amount that could possibly leave the ventricle, albeit you'll learn nowhere close to that maximum amount's going to be leaving. So in ventricular systole, then we are going to have at first the isovolumetric portion, which makes the tricuspid and mitral valves close. And then as we continue that, then we are going to make the aortic and pulmonary valves open. So that will be followed by the part where blood is ejected from the ventricle. And so at the end of ventricular systole, we would have an end systolic volume. So how do we calculate the stroke volume? It's the difference between the ventricular end diastolic volume, which is the starting point because it's bigger, and from that we are going to subtract how much was left in the ventricles at the end of systole, or the end diastolic volume. So this math equation becomes SV is EDV minus ESV, or stroke volume is end diastolic volume minus the end systolic volume. And so this gives us an amount, a volume, milliliters in one heartbeat that leaves the heart. So there are three factors which directly affect this: contractility, preload, and afterload. So preload and afterload, we haven't used those words before, but contractility, we used that word previously when we were talking about inotropic. So those two words are synonymous with us. And generally contractility and preload, as they increase, the stroke volume goes up, and afterload, as it increases, stroke volume goes down. But we'll see why that is once we understand what those concepts are. So this picture is showing preload on one side of the heart, afterload on the other side of the heart, but I want you to realize that preload, what is happening to the right side of the heart, also happens to the left side of the heart. So preload basically is the volume of blood in the ventricles at the end of diastole. So it is that end diastolic volume. And so what can make it go up? Well, if you have a larger blood volume, then you would have more blood going back to your heart with each heartbeat. Or if you had a slower heart rate, then there's more time for blood to enter the atrium, thereby entering the ventricle. So those are the two pretty physiological things that affect preload. So if we look at the heart contractility, so preload essentially is the exact same thing, in case you didn't figure it out, as venous return. The amount of blood that's returning to the heart enters the heart in that one cardiac cycle, and that gives us that preload, or that end diastolic volume. So increasing the preload, in other words, increasing venous return, therefore increases the end diastolic volume, and generally will increase the stroke volume. And stroke volume here is basically represented by the width of the loop, not by the height. Students always think it's a height thing, but it's a width thing. So the loop in the middle is the normal one. And if we increase the preload, yes, we're going to be increasing pressure because an increase in volume increases pressure. But I think you clearly can see that this loop is much wider. So we have a bigger stroke volume. We started with a bigger end diastolic volume. And so we can kick out more blood. And then obviously decrease in preload is going to give us a decrease in stroke volume generally. So if we look back to those 4 components of venous pressure, those 4 components of venous pressure, if you increase them, that increase the venous pressure, then you will be increasing the venous return, which increases the blood flow into the atrium and as well as the atrial pressure, and then that increases the blood flow into the ventricles, as well as increasing the end diastolic volume, or the EDV, and generally the increase in stroke volume. So hopefully now you're seeing how all these things are related. However, we're not going to end with stroke volume. We're going to be going even more. So if you need to go back and review previous slides, go ahead and do that, because this is just going to get more complicated as we go along. And it's really kind of cool, the kind of flow chart you're going to be able to make by the end of this week. So in contrast to preload, let's talk about afterload. So afterload is the resistance that the heart must overcome to circulate blood. And the reason why they're putting afterload on the left side of the heart, because usually we are talking the blood pressure of the blood vessels going to the body, because that's where we have more problems rather than going to the lungs, because the lungs are really close nearby. So if you have increase in blood pressure, in systolic blood pressure, or vasoconstriction, or atherosclerosis, all of those are going to increase your afterload. And before I talk a little bit more about afterload, I want and how it relates to what we've been talking about with stroke volume, I want you to realize that if we increase the afterload, that means the heart has to work harder in order to get that blood out. And if the heart has to work harder, that's called cardiac workload. So you're increasing cardiac workload. And when you increase cardiac workload, that means that heart muscle needs more oxygen. So it's going to use more oxygen. So then the oxygen requirements have gone up. And maybe you just don't have any more oxygen coming in. And so that can give us to a failing heart, which we are not going to talk about right now. But just to let you know how sometimes just an elevated blood pressure can cause dire consequences. So going back to afterload and how it relates to stroke volume. So afterload then is the resistance. So basically we can use systolic blood pressure as a synonym for afterload. And so if we increase the afterload or increase the systolic blood pressure, then the heart has to work harder to get rid of it. And so stroke volume will go low. So here in the middle, once again, we have our normal cycle between pressures and volumes in the left ventricle. If we increase the afterload, we have to generate higher pressures. But what you note is the width is narrower. So stroke volume is represented by the width of the loop. So stroke volume has gone up, pressure's gone up, but stroke volume has gone down. When blood pressure goes up, stroke volume goes down, and then conversely, the opposite occurs as well. So if we look, stroke volume is directly affected by systemic vascular resistance. So an increase in afterload increases our end systolic volume and decreases our stroke volume. So as if we look at the curve between end diastolic volume and the ventricle and stroke volume, it's normally in an upward direction. But this has 4 lines here. If this is the normal, then the 2 lines below it are increasing the afterload, and the 1 line above it is decreasing the afterload. So let's talk about that third effect now that we've covered preload and afterload, and that is ionotropic effect, or the contractility. In other words, the force that the muscle can create at a given length. So if you recall, a muscle can contract like this. So yes, it's contracting, but there's no force behind it. Or it can contract like this, where it's generating a lot more force. And so we had a curve where we talked about, how much overlapping, and so how much contracting, how many cross linkages were going. And so the concepts that we learned in skeletal muscle definitely apply to the heart. So in other words, preload is going to directly affect the contractility. So if we increase the preload, which is the same as increasing the end diastolic volume, that increases the muscle fiber length, which then means that there's more ability for actin and myosin to have more cross links during the contraction, thereby meaning we can have a greater muscle length shortening, thereby we have an increase in contractility or increase in ionotropic effect. Now, that occurs unless the muscle is overly stretched, because as you recall, that only occurs when you're going up the curve, and then we have the optimum length. And then if we were to increase the preload more, it would be overly stretched and the contractility would be plummeting back down towards zero. So that's it for this section on stroke volume. I hope you understood it. Once again, if you have any questions about any of this, please feel free to email or make appointments, and we'll be happy to discuss it with you. So thank you, and I will see you as we continue from stroke volume and go to another concept related to cardiovascular physiology.